Okay, scholars, so here we are in the last portion of Unit 6 Kinetics, and I thought that we would do real quick a review of what we have covered previously before the break. So just real quick, remember that kinetics is all about studying the rates of reaction, how a reaction proceeds, the speed with which it proceeds, and remember for a simple reaction like this, we define rate as either the decreasing concentration of a reactant as time goes on, or the increasing positive rate of change of the concentration of the product as time goes on. So as time goes on, if I made a graph of time and concentration, the concentration of A would be dropping, the concentration of B would be rising, and we define the rate of the reaction as the slope of this concentration time graph, the change in concentration over time, right? So that's the general definition of a rate. It is the quickness with which a reaction is happening, defined as measured as the concentration change over time change. We can talk about this in two different ways. First of all, a differential rate law, is a rate law that relates the rate to the concentration. So how does the rate depend on the concentration? And this is the general form of the differential rate law. This would be for a reaction that has two reactants, A plus B, react together to yield C plus D or something like that. And remember that these exponents have to be determined experimentally. We talked about the method of initial rates, which you need to be very familiar with. And K here is what we call the rate constant, and its units will change based on the order of the reaction. Order of the reaction means what these exponents are, 1 or 2, etc. So if my N is 1, and my M is 1, then I would say it's first order with respect to A, first order with respect to B, second order overall, right? So just some terminology that you need to be familiar with. Those orders matter because we have three different versions of the next type of rate law, the integrated rate law, and we typically like to write these for just a reaction that has one reactant. If it is first order, remember that the natural log of the concentration versus time will yield a straight line on a graph, where negative k will be the slope of that graph, or rather the slope will be negative k. So remember that integrated rate laws are always going to be concentration versus time. Differential rate laws were rate versus concentration. But it's not as simple as concentration versus time for integrated rate laws. It's going to be some manipulated version, the natural log of concentration versus time for first order. For second order, do you remember what it was? It's 1 over the concentration. That makes a straight line with time. And then zero order, that one is the simplest. Concentration and time already yield a straight line. Please remember what you are responsible for. You're responsible for knowing how to take some data, some time, and concentration data, and run linear regressions to see which one fits and determine if a reaction is first, second, or zeroth order, and write the rate law. You're responsible for being able to find K and know the units of K. You can either solve that or memorize it. And remember that you need to know just very generally half-lives. First order reactions have a constant half-life, right? Constant half-life. Second order reactions have half-lives that get longer. No, I'm sorry, they get shorter, don't they? So each successive half-life decreases. And then for zero order, those get longer, so that we get lengthening half-lives, don't we? The time it takes to cut the thing in half gets longer and longer. So hopefully you all feel pretty good about that. And now we're going to proceed to the last half of the last little segment of this unit, which I think we can knock out today. So let's do it. Reaction mechanisms. So here's the idea. Most chemical reactions, actually, we have found through research and experimentation, they actually occur in a series of steps. Those steps we typically refer to as elementary steps. So a reaction will be some combination of elementary steps. I'll give you an example here in a moment. Basically, this is an information slide, and then next we'll be practicing these ideas. So it should make pretty good sense to you here in a few moments. Studying kinetics can help us determine the steps that reactions actually go through to occur. So a mechanism is the term that we give to that series of elementary steps. And in order for a mechanism to be a good mechanism, if you're a chemistry researcher in a lab and you're researching a chemical reaction, you may be interested in finding a theoretical mechanism. What are the steps that this reaction actually goes through? And there are requirements for what is considered to be a good theoretical mechanism that is then going to be verified through experimentation. The first qualification, the first thing that must be true in order for a reaction mechanism to be a good mechanism is that the elementary steps in the mechanism, that's what a mechanism is, right? It's a series of elementary steps, they have to add together to give the overall balance equation for the reaction. Remember when we did Hess's law and we were fitting together those steps like a puzzle piece and we were canceling things out on both sides and adding them up to get the overall reaction? Exact same thing here. The sum of elementary steps have to add together in that same way to give the overall balance equation for the reaction. And then finally, the mechanism has to agree with the experimentally determined rate law. So we already should know the rate law for the reaction, and the mechanism, the steps have got to agree with that rate law. Here's what I mean by that. We have a series of steps. Those steps have got to add together to the overall balance equation for the reaction. And one of those steps is going to be the slowest step. It is going to occur much more slowly than all of the other ones. That is therefore going to govern the rate of the reaction. Imagine these steps like racers on a relay team in a relay race. The whole team is only as strong and as fast as the slowest member. So the overall reaction can only proceed as quickly as the slowest step, as the slowest racer in the relay race. So that step determines the rate. It determines the speed of the whole reaction. We call it the rate determining step. The rate law will always agree with the stoichiometry of the rate determining step. This is all going to make sense in a moment, but here's what I'm talking about. A rate law, differential rate law, looks like this, right? And do you remember what we said the N and the M are and where they come from? Yeah, they come from experimentation, don't they? In other words, if your overall reaction is like 2A plus B yields blah, 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 then this N is not necessarily a 2, that M is not necessarily a 1. You have got to experimentally determine these. But what I'm telling you now is that if you know the steps of the reaction can be broken down into steps, and if you know that one of them is slow, it is the rate determining step, then these exponents can be written from the stoichiometric coefficients in the balanced chemical equation. That's the only time that you can grab these exponents from the equation, is if the equation is for that rate determining slow elementary step in the mechanism in the series of steps. Okay? I know this does not make a lot of good sense to you right now, but I think it will when we do some examples. Okay, so here's our first example. Let's take a close look at this. So nitrogen dioxide reacts with carbon monoxide to produce nitrogen monoxide and carbon dioxide. That is an overall chemical reaction, an overall chemical equation. So my overall reaction is nitrogen dioxide, NO2, reacting with carbon monoxide, CO, to produce nitrogen monoxide, NO, and carbon dioxide, CO2. So there's the overall reaction. And what a scientific researcher has done, what a chemical researcher has done, is propose this mechanism, where a mechanism is, hey, this overall reaction, we think that it actually happens in steps. The steps are like this. Here's step number 1, and here's step number 2. So let's see if this is a good mechanism. Remember, good mechanisms have to do 2 things. They have to add up to the overall reaction, first of all. So let's see if that's true. So looking through here, it looks like I have NO, NO, NO3, and NO. But then in step 2, I get NO3 as a reactant. In step 1, I had it as a product. So those are going to cancel out. And do you see any other reactants and products from step 1 to step 2 that would cancel out? Yeah, I see an NO2, right? So it looks like NO2 cancels out with NO2. And then I have NO2 plus CO on the reactant side, which is just what I want, yield NO and CO2 on the product side, which is just what I want. So yes, this does seem like it's going to be a pretty good mechanism, because my first requirement has indeed been met, that the steps add up to the overall reaction. In other words, reactants and products cancel out, and all I'm left with by the time I've analyzed all the steps is this overall reaction. Okay? Now let's see in another example how all this relates to the idea of a rate law. Okay, so let's look at this example. Here I have an overall reaction. This is my overall reaction. And they're telling me that the rate law is determined to be this. So I know through experimentation that this is the rate law. Here's the mechanism. Step 1, step 2. First of all, let's see if this mechanism makes sense. What has to be true about it to make sense? 2 things have to be true. First of all, it has got to add up to yield the overall reaction. So I can see that I have NO2, NO2 on the reactant side. That gives me 2 moles of NO2. I get 1 mole of F2. So I have all my reactants. On my product side, I get NO2F, NO2F. There's 2 moles of NO2F. That's just what I want on the product side. And then I have just atomic fluorine here as a product, and then again as a reactant. Those are going to cancel out. So yeah, these steps add together to give me all my reactants and all my products and nothing else. So yes, the mechanism does seem to be good that way. That's just what we saw in the last example too. But what we didn't see in the last example now is that there's something else I need to consider. I have got to consider whether or not this mechanism makes sense with the rate law that I know is true for this reaction. What has got to be true about a rate law as it relates to reaction mechanisms? Well, this must fit the stoichiometry of the equations of one of the steps. Is that the case? Yeah, it is. You can see here that NO2 raised to the first power, F2 raised to the first power. Here in this first step, I have 1 mole of NO2, NO2 raised to the first power. I have 1 mole of F2, F2 raised to the first power. That makes perfect sense. So what have I just determined? Well, if this is the rate of the reaction, I know that the reaction mechanism, the elementary step that matches this, must be the slow, also known as the rate determining. It is a slow rate determining step because my rate is based on the stoichiometry of that step, of that elementary step. So yes, this is a good mechanism, and I've just determined, because I know what the rate is, what the rate law is, and that rate law matches one of the steps, I know that this step must be the slow rate determining step. It must be holding the whole reaction back. It must be governing, determining the rate of the whole reaction because it's happening more slowly. So two things have got to be true for a mechanism to be a good theoretical mechanism. In order for me to say that this overall reaction probably does actually happen in two steps, those two steps have to add up to the overall equation, which they do, and the experimentally determined rate law has got to show up in one of the steps, stoichiometrically speaking, raised to the first power, raised to the first hour, first order with respect to NO2, first order with respect to F2, that has got to match the stoichiometry of one of the steps. And that is indeed the case here, and I call that the slow or the rate determining step. All right. Now, unfortunately, it does get a little bit more complicated, which we'll see in a moment. But I do want to take the time now to draw your attention to something special that we didn't talk about last time, this guy right here. You'll notice that here in this slow step, he got produced and then got immediately consumed again. And he does not show up in the overall chemical equation. It is as if he appears and then disappears and then doesn't make himself known in the overall process. We have a special name for chemicals that do that. They are called intermediates. You need to write this down and know it, and know how to determine what an intermediate is in a reaction mechanism. An intermediate, you need to write this down, is a chemical that is produced in one step, but then consumed in another step. It's produced in one step, but then consumed in another step, and thus it never shows up in the overall reaction. It's an intermediate. It's a go-between. It gets created, but then it just gets consumed again, and that's its only purpose, is to get consumed ultimately, and it never shows up in the overall reaction. All right? It's called an intermediate. Later, we're going to see something that works the opposite way. It gets consumed, but then produced again, and you will see that has a different name. But this is called intermediate. It gets produced, but then it gets immediately consumed again, and it does not take part in the overall reaction. Okay? This is the slow rate determining step because it matches my rate law. So right now you should understand what a reaction mechanism is. It's a series of steps. You should understand when a mechanism is considered to be a good mechanism, when the steps add up to the overall reaction, and when the experimentally determined rate law matches, the stoichiometry matches the slower rate determining step. Now let's see how intermediates can kind of make things more complicated for us. Okay, so here's an overall reaction here, and here are two proposed steps. So I can tell you that this is a good mechanism, and let's see why. I want to make sure that these two steps add up to the overall reaction. So I have 2NO and I have O2. Those are both reactants. I have 2NO2 as a product. That's good. And you can see here I get into O2. It's produced, but then it's consumed as a reactant again. So overall, it's showing up on both sides of my yield arrows, so it gets canceled out. And I have a name for that, don't I? That is an intermediate. So my intermediate, I would say, is into O2. It has been produced, but then immediately consumed again. All right. So now I want to write the rate law. And you know that the rate law is always going to match the stoichiometry of the rate determining step. Which one is the rate determining step? Yeah, it's the slow step, right? The whole reaction can only proceed as quickly as the slowest step. So the rate law then would be this: R equals K times into O2 raised to its stoichiometric coefficient of 1 times O2, the reactant there, raised to its stoichiometric coefficient of 1. Remember, the rate law will always be based on the stoichiometry of the rate determining step. These exponents are 1 and 1. First order, second order overall. because the stoichiometry of the rate determining slow step shows up right there with a 1 and a 1. But there's a big problem. Can you think about what the big problem is? Yeah, I've written a rate law that says that the rate depends on the concentration of something that doesn't even show up in the whole process, that the rate depends on the concentration of an intermediate. I don't want that. That is not a good rate law. In other words, N2O2 is my intermediate. It gets produced but then consumed away again and doesn't show up in the overall reaction. I don't want to write a rate law in terms of that. That's going to be a bad rate law. That's not going to help me. While it is technically correct because it is based on the slow rate determining step, I don't want to write this with an intermediate in it. Your rate laws that you get from reaction mechanisms should never have an intermediate. So I need to pause and see if I can replace this with something. Is there something I can replace that with that would make more sense? Well, where did the N2O2 come from in the first place? It came from this fast step, didn't it? It came from 2 moles of NO reacting with each other. So my rate law then is not going to be this. My rate law is actually going to be, I'm going to show where the N2O2 intermediate came from. I don't want an intermediate in my rate law. It came from 2 molecules of NO reacting with each other. So in other words, I'm just taking this 1 mole of N2O2 and I'm replacing it with this equation where 1 mole of N2O2 came from 2 moles of nitrogen monoxide. And then I still have 1 mole of O2 right there. So that is a good rate law. All I've done is I've replaced the intermediate into O2 with something that makes more sense. Where did the N2O2 actually come from? Well, it came from the 2 moles of NO reacting quickly, right? So I'm allowed to write that in my rate law to help me get rid of that intermediate. You should never have an intermediate in your rate law. Okay? All right, let's keep practicing. Okay, this is a great example, and in order to do this, I need to introduce a new concept to you. So, and I'm going to define this a little bit better later. But here we have a chemical reaction, and this chemical reaction involves something known as a catalyst. You'll see I've written that down there. Now we're going to define exactly what a catalyst is later, exactly what it is, but right now we're going to define what it is in terms of reaction mechanisms and reaction steps. You know that a chemical reaction involves a catalyst when on the reaction yield arrow of the overall equation, this is the overall chemical reaction, when a chemical is written above that arrow, so I negative, I've just kind of given it away, the iodide ion right here, I minus, that ion is serving as a catalyst for this reaction. A catalyst, generally speaking, is a chemical that speeds up the reaction process. It helps the reaction occur without getting consumed or changed itself in the reaction. Here's another way of looking at it. A catalyst is just the exact opposite of an intermediate. Intermediates, if you remember, get produced but then consumed again. A catalyst gets consumed but then spat back out and produced again. In other words, it takes part in the reaction, but it doesn't get changed in the reaction. It just kind of helps to facilitate the reaction. We'll talk about that more later. But whenever you see a yield arrow with a chemical written over it, that means that that chemical is catalyzing the reaction. It's helping the reaction happen. Okay? So first thing I want to do is I want to write the rate law for this, where the rate law is going to come from the slow rate determining step, isn't it? So I'm going to say that R equals K, and my rate law is just going to come from the stoichiometry of the rate determining step, which looks like it's going to be H2O2 raised to the first power, and then I minus raised to the first power as well. Now listen, I minus does not show up in the overall reaction. It's written here as a catalyst, but it does not take part in the reaction. So are we allowed to have it in the rate law? And the answer is yes. You are not allowed to have an intermediate in your rate law. Remember last time in the last example, we had an intermediate that showed up. We had to go through and look at the fast step to see where that intermediate came from and replace it. But I do not need to I do not need to worry about that with a catalyst. I can have a catalyst. Writing a catalyst in a rate law is a legal move in the game, so to speak. It's okay to do. My catalyst is I minus. Here's how you can look at a reaction mechanism and right away find a catalyst. First of all, a catalyst will never show up in the overall reaction. It's written here above the arrow to show you, hey, this is a catalyzed reaction, but it doesn't actually take part in the reaction. And a catalyst will always get canceled out in the reaction mechanism steps, but it's the opposite of an intermediate. You need to write this down. A catalyst will get consumed, but then it will get produced again. So, in other words, it gets recycled. It does not end up changing its form. It does not undergo chemical change overall. It's true that it undergoes chemical change in the steps, right? Here it is actually changing to IO minus, but then it gets changed right back to I minus. So a catalyst is the opposite of an intermediate. An intermediate got produced and then consumed. A catalyst gets consumed and then spat back out again, gets produced again. It gets recycled, basically. Okay, so I minus is a catalyst. Do I have an intermediate? I do have an intermediate. So my catalyst is I minus. I'll see if you can find the intermediate. Yeah, my intermediate is IO minus. Why? Because it got produced, but then it got eaten up again. It got consumed again. We do not refer to those as catalysts. They're intermediates. See that these are opposites from each other. The intermediate, you don't end up with any of it, right? It gets produced, but then it gets consumed again. The catalyst gets consumed, but it gets produced again. You actually do end up with it. They're both similar in that they don't show up in the overall chemical reaction. By the way, is this a good reaction mechanism? I see that I've just left something out. Do you see what I left out? Yeah, silly me. This is supposed to have an O2 right here. This is a good reaction mechanism because you can see that I have H2O2, H2O2. I have two H2O2 on the reactant side. I have two waters on the product side, and I have one O2 on the product side. So yes, that is a good reaction mechanism. I have a rate law that goes with the rate determining step. Remember that the rate law will always be written from the stoichiometry of the rate determining step. You can have a catalyst in your rate law, but you will never have an intermediate in your rate law. If you have an intermediate in your rate law, you have to go back and figure out where the intermediate came from. Anyway, please keep straight the difference between intermediates and catalysts. Intermediates get produced, but then consumed again. Catalyst gets consumed, but then produced again. The catalyst gets recycled. You will actually see the catalyst overall. It doesn't take part in the chemical change. It helps, it facilitates the chemical change. You end up with it at the end. You end up with it at the end, but an intermediate you do not. An intermediate, just what it sounds like, it's only present in like the middle. Between the steps. Between the steps I have some IO minus, but after this last step it's gotten consumed again, okay? If you are a chemical researcher, how are you going to know if this is an actual good mechanism? Well, several ways. First of all, as we've said many times, if the steps add up to give you the overall equation, if they make sense based on what you know, in other words, if you know this reaction occurs more quickly and easily with the presence of I minus, if you know that I minus is a catalyst, in the lab setting, it actually facilitates the reaction, helps it occur more quickly. Look, I minus is showing up in this mechanism as a catalyst. That makes sense. Another thing you could do is you could actually force this reaction to happen very, very slowly, and you could actually see if you end up with any IO minus between the two steps. The presence of IO minus between the two steps after the slow step but before the fast step, if you can slow down the whole thing enough to actually get measurements and data about that, then the presence of IO minus that then gets consumed again, would it be a clue? It would be evidence for the idea that this is a good mechanism. Okay, so you guys should be able to evaluate mechanisms, see if they are good mechanisms or not. You should be able to determine intermediates, catalysts, write rate laws based on the rate determining step. If your rate law has an intermediate in it, you have to rewrite it based on the other step. If your rate law has a catalyst in it, that's fine. These are all skills that you guys should be able to do. Make sense? Okay, I just need to give you some quick terminology. I think I've seen like one question ever about this, but you never know. So we have names for some of these types of elementary steps. If an elementary step just has one molecule, we call it unimolecular. If it has two molecules, like these next two examples both have two molecules, either two molecules of A or one of A and one of B, two molecules reacting overall, we call it bimolecular. But if it's three molecules, two of A, one of B, one of A, one of B, one of C, for example, we call it termolecular. Okay, so just keep in mind those pieces of terminology. If you have a certain number of molecules reacting in your elementary step, maybe it's a rate determining step and you can write the rate law. We would say this is a unimolecular rate law. This is a bimolecular rate law. These are termolecular rate laws because the elementary steps from which they are derived, the rate determining steps, involve one molecule, two molecules, or three molecules. So just some terminology for you: unimolecular, bimolecular, and termolecular. I wouldn't worry too much about that. All right, yeah, here we are at the final portion of this. Kinetics is ultimately based on this theory that is known as collision theory. Collision theory basically says this, that in order for a chemical reaction to occur, the reactant molecules have to collide just right with each other. Those collisions provide energy to break old reactant bonds and get the atoms and molecules to form new bonds to make the products. So it's all about collisions. It just so happens that some of these collisions are nice and we end up with nice new things. It's not just like a car crash where you just end up with a big mess. It just so happens that whenever molecules collide, they might form new bonds in new ways to give you new interesting products. Reactions happen because reactant molecules collide with each other, and those collisions have to happen in a certain way. That's what we're going to talk about now. There's evidence for the collision theory. Experimentation shows us that typically reaction rates increase with temperature. This makes sense based on collision theory, if collision theory is correct, because higher temperature means that we get more molecular movement, which means we get increased frequency of collision. So if we have more collisions, more temperature means molecules are zipping around more, they have more motion, more velocity, they're going to be colliding more often, therefore we should get more chemical reactions. But we see that even if we calculate the rate of the reaction based on temperature, the rate is not as high as we would think it is. So why is that? Well, it turns out that there are two major reasons. These are going to be incredibly important. First, activation energy. We've already talked about this. Remember that we drew these graphs. If the y-axis is the energy of the chemical system and the x-axis is the progress of the reaction, going from reactants to products. Do you guys remember that all of these graphs kind of had this bump in them, didn't they? And that bump, we said, was the activation energy. That's the initial amount of energy you have to put in to get the reaction to proceed spontaneously afterwards. So in order to get the chemical reaction to occur, we have to put some energy in. We have to break the bonds of the reactants, right? If we start with reactants here and we're going to end with products here, what has to happen? We have to put energy in, increase the energy content of the system, put energy in from the outside to break those reactant bonds, okay? So this is kind of an old idea. That energy is activation energy, which we give this term E with a subscript of A. So activation energy is the energy required to break those old reactant bonds. And now we can be a little more specific. What happens when we do that is we create like kind of a mishmash of atoms and chemicals that we refer to as an activated complex. An activated complex, sometimes it's called a transition state because it's in the middle of a transition from reactants to products. The activated complex always will show up right here at the peak of the activation energy little bump, because just then is when you have broken all the reactant bonds, but you haven't formed the product bonds yet. So you get kind of this general sort of mishmash of atoms and chemicals. That's what I'm saying here. The activated complex, aka the transition state, is a collection of intermediate structures in a reaction during the instantaneous breaking and formation of bonds. In other words, it's passing through the state from reactant to product. It's like a general sort of mishmash. So one definition of activation energy is the amount of energy required to create an activated complex, to break the reactant bonds and allow the product bonds to just start forming. Okay? Here's what we need to talk about. Where does that energy come from? Where does activation energy come from? Well, you know that we've said in the past that it kind of gets sucked in from the outside. It has to, in order for the system to increase its energy, energy has to come from outside. Well, more specifically, it's coming from remember this graph is chemical energy. Okay, this graph is chemical potential energy. So where does the activation energy, the increase in chemical potential energy, come from? It comes from kinetic energy of moving particles colliding. So this energy comes from kinetic energy of colliding reactant molecules. So activation energy is energy that has been transformed from kinetic energy of colliding particles to chemical energy. All right. Here's a really important idea. At any given temperature, only a fraction of molecules will collide with enough kinetic energy to activate the reaction. In other words, to form an activated complex, only a small fraction of those molecules will have enough kinetic energy to break the reactant bonds, transform that energy into chemical energy, and form an activated complex up here. Remember, bonds have got to be broken. Reactant bonds have got to be broken for a chemical reaction to proceed. We have got to get energy somewhere to break those reactant bonds. Where does the energy come from? It comes from the kinetic energy of these particles moving around and colliding with each other. Those collisions may result in the breakage of chemical bonds. That is the transfer of kinetic energy to chemical energy. But remember what temperature is and what temperature means. Temperature is like a measure of the average kinetic energy. Remember that truly, if I have a kinetic energy graph and my y-axis is number of particles, at a certain temperature, do all the particles have one specific kinetic energy? No, remember that the particles have a range of kinetic energies. Remember those Maxwell-Boltzmann distribution curves we looked at? That at a certain temperature, a collection of particles will have different kinetic energies. A lot of them will have, some average kinetic energy, but a few will have even more than that or less than that. This is a Maxwell-Boltzmann distribution curve. It describes the kinetic energies of a system of a collection of particles at a certain temperature. So what I'm saying is that at a certain temperature, only a few particles, only a certain fraction of particles are going to get that kinetic energy to collide and cause their reactant bonds to break to get this chemical energy bump. This process is only going to occur at a given temperature. Our particles have this distribution of kinetic energies. And there's like some threshold. There's some minimum amount of kinetic energy, so to speak, that particles have to have in order to break reactant bonds. So all of these particles have kinetic energy below that. Even if they collide with each other, they're not going to have enough kinetic energy to break the reactant bonds, form an activated complex, and react. It's only these guys right here that have enough kinetic energy to overcome that threshold amount, collide appropriately, convert their kinetic energy into chemical energy by breaking their chemical bonds. Okay? So here's exactly what I am saying. This threshold energy right here, that is the activation energy. The amount of energy that the particles must have when they collide to break old bonds and form an activated complex, where the activated complex is like that instantaneous mishmash of chemicals before the bonds have finished breaking and before the new bonds have finished forming. So to form the activated complex or the transition state, we have to have activation energy. That comes from collisions of particles at any given temperature, because we have these Maxwell-Boltzmann distribution curves of percentage or number of particles having certain amounts of kinetic energy. We're only going to get a small fraction that will have enough energy, enough kinetic energy, that when they collide, the bonds will break and they'll form an activated complex. By the way, is this an endothermic or exothermic reaction? It's exothermic, right? Because my products end up at a lower energy state, a lower chemical potential energy, so that excess energy must have been given out as heat. Okay, so this is an incredibly important graph. The y-axis is like the number of particles that have that amount of kinetic energy. Let's let this be kinetic energy down here. And this dotted line represents the activation energy. The minimum amount of kinetic energy particles have to have such that when they smash into each other, their kinetic energy will be sufficient enough to break old reactant bonds, right? That always takes energy in. And that energy is, now we're saying, it's coming from the collisions of these reactant particles. So what can I do to cause more particles to overcome that threshold? What can I do to shift this graph? Yeah, remember that in order to shift the graph, I can heat up my system. I can increase the temperature. So here you can see T1. T1 is a lower temperature than T2. So by heating up my particles, by heating up my system, I have now shifted this curve to a new temperature where now more particles, all of these, so before just these particles had overcome that energy threshold such that when they collide, they break their reactant bonds. But by increasing the temperature, I have increased the number of particles that meet that amount of energy. So it does make perfect sense that that the temperature would be tied to the reaction and whether or not the reaction is occurring. And yes, we're about to see the speed with which the reaction occurs. Because by increasing the temperature, I shift my Maxwell-Boltzmann distribution curve over, so now I have more particles overcoming that energy threshold, the activation energy. Okay, so increasing the temperature is one way to speed up the reaction, because I'm giving more and more particles sufficient kinetic energy such that when they collide, the old reactant bonds are broken. They can be overcome. That chemical potential energy can be overcome, and I do get that hump. I do go over the hump on my reaction profiles, those graphs that we looked at earlier. All right, collisions in order to cause a reaction. Collisions, one, must have enough kinetic energy to overcome the activation energy threshold. They have to have enough kinetic energy to break old reactant bonds and therefore overcome the activation energy threshold. But two, they also have to collide in the appropriate orientation. In other words, they have to collide oriented to each other correctly. So this is what this statement right here is saying. in addition to having that sufficient kinetic energy to overcome activation energy, the reactant molecules have to collide with the correct orientation. So in other words, in this reaction between CO and O2, when my CO molecules collide with O2 molecules, there is a wrong way for them to collide. In other words, if they collide oxygen to oxygen, that does not end up resulting in a reaction. But if they collide carbon to oxygen, that does result in a reaction. So not only do I have to have sufficient kinetic energy to overcome the activation energy, but they also have to collide with the correct orientation. So this is very theoretical, right? We cannot actually see these collisions. So how did scientists come up with this? Well, they're able to calculate what the activation energy of a reaction is. They're able to use those Maxwell-Boltzmann distribution curves to figure out how many particles at a given temperature are overcoming that energy threshold. And when they do that, they always find that the reaction still happens more slowly than they would predict. So one good explanation for that is that, well, even if you get particles colliding with enough kinetic energy, like these particles are colliding with enough kinetic energy to cause a reaction, but no reaction occurs. So we need a better explanation. We need one step further. We need another variable in our collision. Not only do the collisions have to be strong enough, they have to be energetic enough, they have to be turned the right way. They also have to be of the correct orientation, okay? So this slide is really important. If you can understand this slide, I think you'll be good. Not only do we have to have enough kinetic energy to overcome activation energy and break the old reactant bonds, not only is that a requirement, but it's also a requirement that we have enough kinetic energy and they collide with the sufficient orientation. Okay, so all of this is closely connected to reaction rates. All right, what we've been talking about. Remember that a rate of a reaction depends on this, where A and B are reactants, and K is the rate constant. Well, it doesn't take a mathematical genius to understand that the higher the K value, the higher the rate will be, the faster the reaction will be. So we may be then interested in, what does this K value depend on? And there's a really important equation called the Arrhenius equation right here that actually allows us to calculate the K for reaction in theoretical terms. A here is some constant that has to do with the orientation of collisions. E is Euler's number, 2 point whatever, that E from your math class. EA is activation energy, R is the gas constant, T is the Kelvin temperature. Here's another way of writing it if you take the natural log of both sides. Really doesn't matter. Listen, you don't need to understand this Arrhenius equation. All you need to understand is that the K value, the rate constant, which in a large part determines how quickly a reaction proceeds, is tied to everything we just got done talking about. Okay? It is tied to activation energy and temperature. So let's say you're looking at a chemical reaction and it has a large activation energy. What is that going to, what effect will that have on the rate of your reaction? Of course, it's going to make the rate slow. It's going to slow the rate down because there's a big energy threshold that has to be crossed. So larger activation energy means a smaller rate constant and therefore a slower reaction. That makes perfectly good sense because larger activation energy means that there's a bigger energy threshold for you to overcome. What about temperature? Well, if you know your math, having temperature here in the equation, if you increase temperature, you're going to end up increasing K. That makes perfectly good sense. For chemical reactions, a higher temperature means you get more collisions and more energetic collisions. So of course that's going to increase the rate of the reaction by increasing K. You guys need to know this. You don't need to know it mathematically necessarily. You do need to understand it conceptually and why it makes sense based on collision theory. Okay? Bigger activation energy, more energy threshold, we're going to have a slower reaction. Larger temperature, we have more collisions, more energetic collisions, we're going to speed up the reaction. That changes the K value. All right? Okay, we're almost done. Let's talk about catalysts. A catalyst is, as we've seen in our reaction mechanisms earlier, a substance that increases the rate of reaction without actually being consumed or taking part itself in the reaction. Here's what you need to know. A catalyst works by lowering the activation energy. It does this by facilitating, well, that's a big fancy word for helping, right? Facilitating collisions. It helps particles collide a bit more easily. So it lowers the activation energy. Listen, there's a big misunderstanding that catalysts add energy to help the particles get up to the activation energy. That is not correct. Catalysts do not add energy to the reaction, okay? Many people have missed really simple multiple choice and free response questions in the past by erroneously stating that catalysts add energy to the system. No. Instead, what they do is they decrease the energy threshold. They lower the activation energy and make it easier for the reaction to occur. All right? Two different types of catalysts, homogeneous and heterogeneous. Really simple, a homogeneous catalyst means that the catalyst, I wouldn't even worry about these terms if I were you. Catalyst is in the same phase of matter as the reactants. What do you think heterogeneous means? Yeah, they're in different phases. One really important example of a heterogeneous catalyst is a metal sheet. So this is how something like your catalytic converter in your car works. It helps to convert some noxious fumes into less toxic fumes, basically. A sheet of metal, like platinum is a good one for some reactions, basically is it provides a location for these gas particles. I don't remember the exact reaction, but it provides a location for these gas particles to like get stuck on the metal, and therefore other particles can come and collide with them more easily. That would be an example of heterogeneous catalysis, because the metal, of course, is a solid, and these gas particles that come and stick to them so that other things can collide with them, of course, are in a gaseous phase. So those are in different phases. You guys have probably learned about catalysts in your biology class. Enzymes are catalysts because they kind of can put pressure on a chemical and cause it to break, or they can bring certain parts of the reaction system together and cause collisions to occur that way. This is a really important graph. These are those reaction profiles that we've been looking at, where on this side you get reactants and on this side you get products. What's it called up here? The activated complex or the transition state. So of course this bump represents activation energy. This dotted line represents the reaction with a catalyst. So remember, what do catalysts do? They just lower the activation energy required. Okay? Here's another way of looking at it. This is a Maxwell-Boltzmann distribution curve. All right. So the x-axis is kinetic energy. The y-axis is the number of particles having that energy at a certain temperature. So this right here could represent the energy threshold, the activation energy for a reaction. Only these particles have enough energy to overcome that, break their old reactant bonds, and react. We said that one way we could change this whole situation is by increasing the temperature. Increasing the temperature would cause a new curve, which is shifted over to the right and flattened out a little bit. And so there you can see that, of course, now we have more particles sufficiently reaching that threshold of energy. So again, T1, T2, T2 is greater than T1. You guys need to know how temperature affects these distribution curves. Raising the temperature causes it to shift over and flatten down. We get more particles having more sufficient energy to overcome that original activation energy. But there's another way that we get more particles to collide. That other way is Adding a catalyst. A catalyst doesn't change the temperature, it doesn't add energy to the system, it just shifts this threshold. This new activation energy is with a catalyst. So now you see that the catalyst has shifted the energy threshold down, lowered the activation energy. Now, of course, we have more particles. All of these particles have sufficient energy to react, overcome the activation energy threshold, which has been lowered, and take part in the reaction to form an activated complex and get over the activation energy bump, so to speak. All right, so this has been Unit 6 Kinetics. We are going to talk about this and work through some example problems in your homework packets. You guys need to be working on those homework packets, and I believe that we're going to have an exam on Friday, maybe. An exam this week over this stuff. So we'll have plenty of time to review. We're going to do some more things, and we'll have some meetings and things, of course. So thank you all, and good luck studying.